So, I welcome you to this live session for the course VLSI Physical Design. Now, the course is already halfway through and I hope that you are enjoying this course. We have been receiving queries and interactive comments on the forum, and we are trying to address them to the best of our knowledge. And for this live session, we have already received a few of the queries from you. Let me try to address them first, following which if there are any interactive live queries, we will take them up subsequently. Okay. So, the first query I had, this was an interesting query, or you can say a comment, which of course is a little beyond the scope of the present course. I have not discussed this as part of this course. This is relating to optical interconnects. Okay. The question was, what is the scope for optical interconnects at the chip level, how to implement it. Now, see, we use optical interconnects for high speed communication. As you know, if we send signals over photonic waves, speed is fast, there is very low interference, noise effects are minimal. So, there are a number of advantages, but there are still some challenges, because we have to implement everything inside a chip. Inside a chip, you have to have different optical components like optical waveguides, optical fibers, lens, mirrors, sensors and so on. You see, when we transmit some signals through optical means, what we do? There will be a transmitter, there will be a receiver. At the transmitter side, you are sending the signals using optical waves, using some kind of modulation, and using some kind of an optical waveguide, the signal is moving in the right direction. It can be an optical fiber, it can be some other kind of medium. Similarly, at the receiving end, you have to receive the signal, you have to decode it, convert it into from optical to electrical signal and so on. There are a number of advantages. Now, the state of the art is that there are some instances where this technology is being used in some chips. There are high speed chips where these technologies are already being implemented at present. Okay. So, it is not that it is still in the lab scale, it is a research thing, not yet implemented in practice, not like that. There are a number of commercial chips where limited scale optical interconnects are being used. Now, I am just showing you the basic concept here. This is just a schematic diagram here I am showing you. Now, whatever is shown here, everything will go inside the chip. There will be a light source, which can be a laser, which can be an LED, infrared, any kind of wavelength you can think of. There will be a suitable modulator, and there will be some kind of a layer on the chip through which the light can flow through. That is the so called optical waveguide. At the receiving end, at the other side, there will be some kind of a photo detector, which will be detecting the presence or absence of light, and there will be some filtering stages, following which you get back the data that was sent by the transmitter. Now, this driver and receiver, they are basically logic circuits, and there are a number of things. These yellow blocks, these are the so called optical components. This is the main challenge. On the same chip, you have to implement some components which are electrical in nature, which are very well known and mature technology. On top of it, you have to also put in some layers where some so called optical components like modulator, optical waveguide, photo detector, etc., have to be fabricated and implemented. This is the basic idea behind this optical interconnect. And to answer your question, there are example chips where optical interconnects are being used. Of course, you may say that we are not using it in that large scale as yet, because All fabrication facilities are not yet tuned to this technology, but hopefully this will pick up with time. Okay. The second query, this was a common query, a number of you was having this confusion. You were saying how come buffer reduce the delay of an interconnection line, because in a buffer typically we have two inverters in cascade. So, they will be having some propagation delay. So, putting a buffer should increase the delay, right. So, how come the delay is decreased? So, let me try to give a justification here. Let us suppose I have a source here and I have a destination here, and they are connected by an interconnection line. The length of this line is, let us say, L, right. L is the length of the line. Now, because of RC parasitic effects, it can be shown that the delay of a communication line is roughly proportional to the square of its length. So, you can say that for this line the delay will be proportional to L, which means approximately equal to some constant multiplied by L, right. Now, let us see what we do. We insert a buffer in the middle of this line. Let us say that same source and destination, we insert a buffer in the middle. So, this first part, the line length becomes L by 2, here it becomes L by 2, right. So, what will be the delay in this case? First, let us compute the delay of the interconnection lines. First line of length L by 2, second line of length L by 2. So, again using the same formula, okay, this will be square, I am sorry, length square, so it will be K L square. So, delay will be K into L by 2 square plus again K into L by 2 square plus delay of the buffer, let us say delay of buffer, let us say dB, delay of buffer. Now, the first two terms, if you simplify, this becomes K L square by 2 and add to it the delay of the buffer. So, you see that just the interconnection line delay has gone down from K L square to K L square by 2. Now, for deep submicron technology, this interconnection delay dominates the gate delays. For relatively long interconnection, this K L square is much larger than the delay of two inverters. So, whatever this dB is here, this dB is much smaller than K L square by 2, because of which we say that if we split a line into two or more segments, the overall delay what we show here will be smaller than the original delay K L square. This is how the justification comes, right. Okay. Okay. There was another query relating to clock skew. This question says decreasing the clock frequency may reduce the risk of clock skew. Decrease in frequency means time period is increased, by which the sub-circuit which is far from the clock might also produce well defined stable state before the clock time period ends. Well, whatever you have said, I do not disagree, you are correct, but let me just explain this in a little more rational way. Suppose I have a clock source out here where the clock signal is being generated. This is my clock source. Now, from the clock source, the clock is being distributed to various clock sync points. Let us say, let us consider 2 points, let us say one sync point is out here, one sync point is let us say out here. Let us call this as point A and let us call this as point B. Suppose the original clock was like this. let us say, show just one. Now, this clock signal will reach point A after some delay, which will be the delay of the communication link. So, you will get something like this at A, right. With some delay, this signal will be coming. Now, the delay at A and B may be different, because of which we have this clock skew, right. So, at B maybe the delay is a little more. So, B, the edge is coming, clock edge is coming a little later. So, these are not coming together. Now, the point is that if you have edge triggered flip flops at A and B, then and if the edges do not come at the same time, then obviously the flip flop at point A will get the data stored before the flip flop at point B. But whatever you have said, I am not disagreeing. If the time period is very high, then even if there is a mismatch in the edge, you are saying that I have already given sufficient time for the signals to settle down. So, whenever the clock edge comes, the signal must have settled down. So, we must have been latching the correct signal. But you think of a scenario where between A and B there are also some circuitry. This A is latching some data in a flip flop. From the output of the flip flop, some signal is coming through some gating logic to the input of B. So, maybe there is some kind of a gating circuit, it is coming to B. Now, because of this skew which is happening and they are not happening at the same time, so the old value might disturb this new value. So, finally, whatever will be storing in B might be incorrect. That is the main problem which may happen, right, if there is a clock skew, and this will be independent of the clock frequency. So, however slow can the clock be, this difference in the edges will always be there. So, when an edge comes at A, the edge at B will be coming after some time, and because of the delay and because of the circuit between A and B and this gating circuit, so whatever is getting stored in B, that might become incorrect. That is what the problem is, right. And so, I hope I have been able to explain this. Let us move on. There is a query regarding power routing. The question was, the width of the segments will vary, that is what is said, but the question is why and how. You see, the thing is like this, you assume that here you have a chip, here, let us say from outside you are supplying the voltage, let us say you are supplying a positive voltage, let us say VDD, you are supplying ground, and these VDD and ground are going to different parts of the chip. Suppose there is a single pin VDD, single pin ground. So, what I am saying is that when this signal enters the chip here and here, the amount of current that will be flowing here, that will be equivalent to the total current taken by the whole chip. But what might happen from here is that there may be one line going to one part of the chip, one line going to the other part of the chip. So, if the thickness of this line is T, then the thickness of these lines can be T by 2, because the current will get distributed. You say thickness of a wire, why we make a wire thick? A wire we can make thick so that it can carry more current. Thicker the wire, the current carrying capacity will increase. Now, inside a chip, from the point where the supply voltages or these pins are entering the chip from outside, the maximum current will be flowing at those points. So, the wire thickness at those points will be the maximum. But as we go through again from here, there will be some division, they will become even thinner. So, as this power supply tree proceeds, the lines will become thinner and thinner, right, because of which the width of the wire segments are not constants in power routing, they vary depending on the amount of current that is likely to flow through those wires. Right? Unnecessary, why would you make all the wires thick, right? This is the idea. Okay. There is one query, again I have not covered this as part of this course. There is a standard keyword called ECO, which is the short form for engineering change order. So, the question was what is ECO basically. Now, ECO, engineering change order, is a process through which you are making some change to an existing design. You have an existing chip design, you are making some small changes somewhere. Now, the point is that if we make a small change in a design, do we have to redo the whole design or do we have to make some small changes somewhere? You see, when a design gets fabricated, when a chip gets fabricated, you must have been knowing that there are some masks, layout masks. Using masks, layer by layer fabrication is carried out. Now, creation of these masks are very expensive, this is a very expensive process. Now, if you find that this change that you are trying to make requires only change in the metal layers, only the metal masks, then all the lower layer masks will not change, only a few of the masks change. Depending on that, you will have to decide what minimum changes are required to affect the design change as requested. This is roughly known as engineering change order, and this is a very elaborate process, not so simple as I have said, but roughly it means this. You try to optimize this change, how this change has to be done, so that the cost implication becomes minimum. You can do it with minimum additional cost. Okay? Fine. Well, there was a couple of queries regarding summer internship, that if you do this course, do you get any opportunity for doing summer internship? Well, NPTEL provides you with a facility. It is like this. This is for the toppers of this course. The students who top this course get very high marks. They get an opportunity to do internship in some of the elite institutes like the IITs. Okay? This is organized by NPTEL directly, but even beyond that, all IITs and other institutes also, they have some internship provisions, internship programs. You can apply directly, you can contact the professors, you can apply directly. They usually take interns during summer and winter times. So, if they are available, if they are free, if they are willing to take you, then you can just avail of that opportunity even without going through that NPTEL channel. But NPTEL channel, if you score well, there is some kind of a guarantee that there is very good chance for you to get an internship in a good institute. That is the idea. Okay. There was another query, they said that while filling the form at the beginning, it was mentioned that NPTEL will share our names with the recruiters. Could you confirm whether we get an interview call after this course? The answer is no. No one will call you for interview based on the fact that you just NPTEL shared your names. It is just a database that some companies create. When you later on apply to them, they can verify whether you have done certain courses, done certain trainings and so on and so forth. But above everything, they will check how much you have learned, how well you know this subject, how well you know this course. So, learning is most important. The recruiters will definitely judge you by how much you know, how much capability you have, whatever this course was supposed to teach you, how much of that you could grasp. That is the idea, right. Okay. And we have received some more questions after. Let me see what these questions are. Okay. One question is how we can have experience of there are commercial tools from companies like Cadence, Synopsys, Mentor Graphics and so on. Those are the ones which are widely used in the industry. And when you approach an industry saying that I know physical design, they will definitely ask you what tools do you know, what kind of hands on you have experienced on those tools. Now, obviously, these tools are expensive, these tools are not available everywhere. So, in your institute you can find out whether such tool access facilities are available. If so, then you are possibly lucky, you can have access to the tools, you can have some hands on sessions with them. That way you can learn this physical design flow in the best way, that is the best way to learn. Well, otherwise, well, we have put in some supplementary videos, you can have a look at them, just you can watch them, it will be a one way thing, that you are listening to someone who is talking, but you are not doing it yourself. But doing it yourself is most important, there is no substitute for that. Okay? That is one. And is there any practical in the course further? You see, whatever supplementary video lectures have been provided along with this course, that is all we have. There we have some hands on with the Cadence and other tools, whatever for static timing analysis and other things. So, you can have a look at them. So, whatever relevant things we thought that are important as part of this course for you to know, for you to understand, we have tried to put them as supplementary materials. But of course, there are many other things. It is not possible to cover all the tool flow details in the course, it will itself be a separate course, because the tools themselves are very complicated, very complex. There are thousands of facilities in the tools. So, once you have the tools in front of you, you will have to burn your fingers and learn them yourselves, that is the only way to learn, right. Okay. There was another question on 3D IC and 2D IC, physical design are completely different. Yes, to some extent the process is different. 2D IC, the way you design, you look at it in a monolithic way, it is one way. But 3D IC, you see, again for 3D IC there are two things. One is the traditional 3D IC that are being fabricated, and another way is, it is an upcoming thing, 3D monolithic integration. Normal 3D IC means you put several devices one on top of the other and then you glue them together in some way. Well, here the physical design process is very different. Here the different, you can say, macro layers are fabricated separately, then they are glued together, and when you are gluing them together, they will be interconnected using some kind of via connections. They have them some properties, they have them some kind of parasitic effects. You will have to analyze them. For that purpose some tools are available. Okay. And talking about 3D monolithic integration, well, I do not know of any commercial chip which have really been built using that. 3D monolithic integration says you do everything from scratch and develop the chip in a, like you are building, you are making a building, floor by floor you are making it. That is called 3D monolithic integration. You see, the idea is like this: at the lowest level you will be having some logic circuits, maybe using CMOS, on top of which you may be having some memory, on top of which you may be having additional layers of memory, on top you can have some sensors, you will be building an entire system on a single chip, layer by layer. Now, for 3D monolithic integration there are some challenges. When you are fabricating the higher layers, you are not allowed to use any high temperature process, because if you try to do that fabrication at a high temperature, the lower layers might get damaged. So, one inherent requirement is the upper layers whatever you are using, they must be lower temperature processes. Well, technologies like carbon nanotubes and etc., which you have been hearing, they are coming, they are examples of low temperature processes. So, maybe future chips you will see using this kind of multi layers. You have something called resistive RAMs, resistive memories. They can also be fabricated at low temperatures, they can be available in the upper layers. So, like that you can build a multi-tiered chip like that. Okay. So, let me see if there are any other queries. Okay, just a second. Yeah. See, static timing analysis naturally helps you with lot of timing related issues to get identified in a design. If you say limitation, you see limitation means the accuracy of static timing analysis is limited by the accuracy of the models you use to model your building blocks, because what you are analyzing? You are analyzing a netlist consisting of some building blocks and their interconnections. How accurately you are modeling the building blocks, how accurately you are modeling the interconnections. So, the overall accuracy of the whole static timing analysis process will depend on the accuracy of that. So, more accurate models you are able to use, more accurate will be the your ultimate result that you get out of this analysis. Okay. Recent trends in metallization optical interconnect method to implement. I have already mentioned about optical interconnects. I do not have anything to add like that, because I am not an expert in optical, in photonics and other things. That is totally in the photonics domain. People are working on it. Normally, inside a chip, no one is saying that all interconnections will be done using photonics, not like that. There may be two cores, cores means two subsystems inside a chip, they will be interconnected using high speed photonic interconnects. That kind of a architecture people are talking about, right. Can you give exposure of physical design? I do not understand this query. What do you mean by can I give exposure? You will have to sit in front of a computer, use the CAD tools, then only you can have exposure. You have to have access to these CAD tools, but unfortunately we cannot provide you with that access. You will have to see whether in your own institute or in your own organization where you work, there are some facilities of accessing those tools. If they are available, then of course you can use them, otherwise I think it is very difficult, because these tools are very expensive or specialized, and usually these are not available for anyone to use. Those are very restrictive. So, I think some more questions are there. Cloning process to remove setup violation, this we can discuss little later, because I think let us cover a couple of weeks of lecture, maybe in the next live session that we will be conducting, we can talk a little bit more of it, because these are things which I have not covered in the class, in the lectures, but if you are interested we can have a discussion on that later, but I think it is a little early now to discuss this thing, cloning process to remove setup violation, because cloning, I just mentioned cloning, that some gates you can replicate. You can replicate some gates instead of using high fan out. Like the idea is that, I mean just very briefly let me tell you, suppose I have a gate, instead of having high fan out, so what I am saying is that instead of doing this, you replicate this gate along all the paths. something like this. So, instead of using the fan out and the output of the gate, you use the fan out in the input of the gate using something called cloning. So, that sometimes helps. There are example, I do not have examples right now to tell you. Well, what I will do, I shall try to post some examples on the forum. You look into the forum, we will be accessing, we will be just posting that within a few days. Some examples where I will show that this cloning can actually really help you in reducing or eliminating this kind of timing violation to some extent. Okay? Fine. And yeah, something else. Static timing analysis for analog blocks, it is very difficult. For analog blocks, you cannot do static timing analysis, because the way you analyze analog blocks is totally different. You do not analyze analog blocks with their signal transitions or delays. They have some other properties like you can say bandwidth and so on and so frequency and so on and so forth. You cannot use STA for analog blocks. Analog blocks is a different ball game altogether. And another thing I would like to just add to it, in the assignments you must have seen that sometimes there are some ambiguities, some mistakes, some errors. Well, although we have tried to make the assignment in such a way that there are no errors, but as you can see that sometimes some errors do creep in. So, we try to take care of them. If some questions are so erroneous or ambiguous that you cannot do anything about it, we withdraw it from evaluation. Some answers, if there is some confusion, we try to correct the answers and re-evaluate them. We ask the NPTEL to do the re-evaluation and update the marks correctly. Of course, they will take some time to do that, they do that with that time, and it will be done ultimately. And regarding the final examination, the type of questions that will be asked will be very similar to the kind of questions you see in the assignments. So, if you go through the lectures and solve the assignment questions, follow them properly, it should not be too much of a problem for the final examination. So, I think you are already halfway through this course. So, we expect to have another live session for this course later. Okay. So, in that course, whatever other doubts get accumulated, we can have a discussion there. So, I wish you all the best. So, you be active on the forum, you ask whatever questions you have, whatever way we are able to respond, we shall try our best to do that. Okay. So, be active on the forum, that is very important. Thank you very much. Question has come? Okay, okay, just a second. There is another question. Just a second. Why substrate in NMOS is connected with ground and PMOS with VDD? Well, that is a device level question. So, you read any basic textbook on MOS transistor fabrication. I can suggest a very basic book by Pucknell and Ishagrian, that is clearly mentioned why you need to bias the substrate with a particular voltage. So, if you do not bias the substrate with that voltage, the channel will not be formed properly, that is the main purpose. But I suggest you read the book. I cannot explain whatever is there in that entire chapter in this short session, but the basic idea is that if you do not bias the substrate with a proper voltage, for an NMOS transistor the channel has to be N type, electrons must flow through the channel, right. That is why for that you connect the substrate to ground, but for PMOS it will be different, holes are supposed to move, you connect the substrate to VDD, that is how it works. Okay. Thank you.